Hello, this is ME6008/6122 microphysics for the University of Limerick. This is our next lecture. We're going to cover the general correlation for arbitrary shaped channels. So previously what we covered was the Fourier derivation of the fully developed rectangular velocity profile. And that was quite a hairy looking equation that we had. And what we're moving on to now is a general equation that we can use to calculate the pressure drop for a given flow rate in a arbitrarily shaped channel. And this derivation is really coming from these guys, Muzychka and Yovanovich. So there's a paper based on this from 2009 that I've actually uploaded onto Sulas. So that's the original paper, and you can read through this. So what I'm working through here is going to be a synopsis of that paper. But if you can read through the detail of that, you won't need to per se, but it's good to read those kind of papers anyway. I think Yuri Muzychka is still over in Newfoundland. He actually spent some time in UL with us for a few months, a few years back. Yovanovich as well is quite well known in the fluid side, so it's a very good paper, and it's pretty useful to use in calculations. So the first thing we're going to cover is really talking about this idea of what is the appropriate length scale to use, and generally with if we take a circular pipe for example, it's pretty obvious you go for the diameter. So if you have a kind of a wonky shape like a rectangular shape and you're trying to pick, well, is it the width or is it the height or what's to be used? What's often recommended is to use the hydraulic diameter. We see the derivation for that here. Okay, so the factor of 4 comes in here because we've got 4 times the area over the perimeter. And if you put in the area of a circle as pi d squared over 4, so the 4 here cancels out that, and it gives you the equivalent as a circle. So if you have a rectangular shape, it ties it all together to be consistent. So that's the idea with having the factor of 4 inside there. And again, you can see this kind of makes sense because we've got it's first of all it's tying circular stuff which we're used to in the macro scale is pretty common geometry with rectangular stuff, and using the cross-sectional area to the wetted perimeter, it's given us where the pressure force is tied to the cross-sectional area, and then the shear force is linked to the wetted perimeter. So it's capturing the relevant geometry that is tied to both those two forces that are at play in fully developed flows. Now, what is found is that it actually doesn't work the best, and the criteria for it to be assessed is, if you take kind of any arbitrary shape and you use this as a length scale, well, then if we're doing the Poiseuille number, so if we do a friction factor times the Reynolds number, we should have a constant. Then all those constants should be the same. And what you'll find is that if you look up the literature for a Reynolds number for different shape channels, you have different constants. So just to kind of explain it a bit, if I swap over to a blank slide, I'm writing this by hand, so we'll see how it works out. Well, essentially what we have is for a circular pipe, take to be 16 over the Reynolds number is the pressure, is the friction factor. Okay, so that gives us F friction factor times the Reynolds number is equal to 16. Now, if you swap to, that's for a circle. If you swap to a different shape, you get a different number. So we'll call it C over RE because I can't remember what it is. I'd have to look it up. You'll see it in fluid mechanics textbooks. So the friction factor times our number is some constant C, and if you change the shape of it, so we'll make it, say, a rectangular one, you've got, let's bring it over here, F is B over the Reynolds number. Because every time you're getting a different constant. Okay, so we've got B, we've got C, we've got 16, or some kind of a number or whatever. And what we'd like to have, if we had the correct length scale today, is that, well, we just have one number, one constant for the product of the friction factor and Reynolds number, which we call the Poiseuille number. Okay, so that's the whole idea with that. So I'll just swap back to our slides. Okay, so now what Muzychka and Yovanovich are recommended is that we use the square root of the cross-sectional area. And that is found to work quite well. And we will see that in the correlation that we use, that they're using this as our length scale for the Reynolds number. So it's not the diameter of the pipe, it's not the longest dimension or whatever, or the hydraulic diameter. It is the square root of the cross-sectional area. There's a bit of a discussion in White's textbook. I think it's in any edition of it. If you happen to have one, you might find one online. I don't think it's accessible remotely through the library. It's a physical book. But I'm pretty sure there are PDFs out there on the web. I've been able to find a good few of textbooks. I'm not sure how legit they are. They probably violate all the copyrights, but you can see stuff written up on the web for PDFs of White's book. And he recommends this as 0.64 times the hydraulic diameter as an appropriate diameter to use. In turbulent flow, this works quite well. For some reason, and I'm not an expert in turbulence by any means. I don't find it particularly interesting. It's kind of just a brute force computational stuff. But the hydraulic diameter seems to work quite well in turbulent flows, and for most macro scale stuff is turbulent anyway. So we're going to the special case, and we're in laminar flow, so we're going to be using this as our length scale. Just to look at a bit of scale analysis, so we go back to our force balance. We have the pressure forces and the shear forces. So we have this area of perimeter, so that's where it's coming from. If we do some scale analysis on that, so again, you'll recall from the scale analysis we've done before that our shear stress is mu to tu the y squared. Okay, so that's our shear force. So if we put in the length scale for that, then we have our pressure force. Okay, so we scale with that. So we substitute in and we end up with this as our effective length scale. Okay, so it does make sense in fully dialed flows to have a kind of an area to perimeter one, but it just turns out it doesn't work particularly well. Now, what we're going to do is we're going to look at two cases. First of all, the fully developed case, and secondly, the developing case. And in the fully developed case, so this is where our velocity profile is fully developed. So it's not changing as we move along the length, and that was the case, the scenario that we analyzed in a rectangular channel. What we have is that the Poisson number is constant. In fact, there's an F missing here. If I can, then F times RE effective is equal to C1. Okay, so there's a typo there on my slide. Okay, so our friction factor is defined as follows. So it scales at 1 over the Reynolds number with our effective length scale. So we would expect some kind of expression of that form. So that's pretty straightforward. And we have that for the length of the channel being very, very long, quite longer than the entrance region. Okay. In developing flows, the force balance that are taking place is inertial with friction. Okay, so we no longer have the pressure being the dominant force as we have. Here we have in developing flows, we have pressure versus shear or friction. Here we've got inertial versus friction. And we do our scale analysis, and we've done this in a tutorial sheet, so you'll be familiar with this already. We end up with this result for the slenderness or aspect ratio of the boundary layer. Now, if we take that expression, it is expressed in terms of L, okay, which is the channel length. And what we're going to rescale it into L effective. Okay, so how we do that is we just multiply across by L effective over L effective, so effectively by 1. And we end up with this kind of hairier expression. So we just define that as L plus, and we end up with this result here that delta over L effective scales with the square root of L plus, where L plus is this term. Now, it turns out that L plus is a pretty convenient term. It doesn't look it there at the moment, but it's very readily defined and very readily measured, so it's actually quite useful. So we'll come back to that in a few minutes. But although it looks very, very complex here, this actually definition of L plus, sorry, this one here, it's just marked in red. So this definition here of L plus is actually really convenient, even though it doesn't look, it looks a bit convoluted at the moment. But it's a pretty straightforward thing that can be readily measured, and that makes it an interesting engineering parameter. Again, if you think back to, defining characteristic length scales as engineers, we go for a diameter rather than a radius. So we talk about the area, I've said this in first year stuff, where we talk about the area being pi d squared over 4, not pi r squared, because a diameter is readily measured, whereas a radius is actually quite difficult to measure. Okay, so if we drive on, then what we get is that our friction factor times the rescaled Reynolds number scales at 1 over root L plus. Okay, and this gives us this summarizing result that in the fully developed region, so if I just change the color, purple, sure. So this bit here is fully developed. Right with the mouse. Fully developed, and this is developing. Okay, so we have two terms: the friction, or sorry, the Poisson number based on the L effective length scale, which in our case is going to be the square root of the cross-sectional area, is a constant in long channels where we're much longer than the entrance length. So LH here is the entrance length. And if we're inside the developing region, so the flow has not become fully developed, so our length is shorter than the fully developed entrance, or sorry, the entrance length, then we have it as some constant divided by the square root of L plus. Okay, so if this scales with 1 over root L plus, then the friction factor is equal to constant times that. Okay, so that's our two conditions. And what we want to do now is to join those together. Okay, so I'll skip that for a second. I just want to note a correction on this. There's a typo on my equation. Okay, so there's a bracket around this term here, so just be careful of that. You'll see it in the original paper. I actually couldn't edit this because this is a PDF, and on my laptop I don't have a PDF editor on it, so I'm kind of stuck scribbling over stuff. But it's something I had intended fixing. But with the shutdown, obviously, I've lost access to quite a number of resources. Okay, so what we have here is a combination. We have our friction factor times the Reynolds number, where we've used our new length scale. So L effective is equal to square root of the cross-sectional area. Right, so that's our length scale there. And it's made up of two terms, the developing term and this hairy looking term, which is the fully developed. So if you look at this term, all it has is epsilon inside it. And epsilon is an aspect ratio. So it's a geometric feature. So all of this is really just a constant that factors in the geometry that you're looking at. Okay, so that is the fully developed portion of the expression. And this bit here is the developing section, okay, the entrance region to the channel. Okay, so what we have are two sections that are combined. We have the developing section here. Just change color on this. So that's our developing, and this is our fully developed. And what we're doing is we're blending into one unified correlation the two terms. So what's done here is an asymptotic solution. And again, this is going back to paper from the 70s of Churchill and Usagi, where the main was that developed this technique. And it's a mathematical approach of if you have two asymptotic solutions. Now let's see if I can move to a blank slide. We'll just draw an axis, and I'll put in two curves. So I got one like that, and the other one like that. Okay. So essentially what you're doing is we got two conditions on this, and we're going to blend the two together. Okay, so we're going to merge the two. And what we'd have is we'd be plotting experimental data, and we'd be getting this kind of behavior. This be, say, for the developing region. Okay. So we'll call that FRE root A. Okay. And so as we move along, and this may be L plus. Okay. So this then becomes constant. And we have a load of data points along here as well. And we have a functional form of this, we have a functional form of this, and we want to blend the two together. So an asymptotic approach is a way of doing that. So what you do is you take the first term, which would be A1, we call this A2. So it is A1 to the n plus A2 to the n, all combined to the power of 1 over n. And what you do is you just kind of cycle through n to see, okay, how does it fit the best? So you start with n equals 1, because that's the easiest. Then you go n equals 2, and see, does that work? Or does n equals 1.5 work? Or, you know, whatever works, and you kind of cycle through it and get your best fit for the data. So when this is done, if I just go back to the equation, when this is done here, those we'll swap on to red. You can see we got 2 here and 1 over 2. So that's our n equals 2, 2, and 1 over n here. Okay, so that's a way of combining these two together into one expression. All right, so it's a particular mathematical technique. So just be careful of that. It's root epsilon times 1 plus epsilon in brackets times this thing here in brackets. So just be careful of that. I'll see that bracket is gone. So I just made a mistake when I was writing that equation. All right, so what this gives us is a general expression for calculating the friction factor for any arbitrarily shaped channel. Again, why is that useful? Because in microfluidics, although we might like a particular, you know, a rectangular cross section or a circular one, you know, we get something wonky like this, the shapes through there, for example, or you'll have curvature, you know, with kind of more elliptical type shapes and stuff like that. And this is a way of calculating it. And again, typically in the stuff you would have covered in fluids already, we tend not to consider the pressure drop due to the entrance region or where the flow is becoming developed. In microchannels, depending on the flow rate, you don't know whether that is important. And very often we have quite small conduits interface with longer ones, and there may be a pressure drop contribution that is dominated by this term in some portions of the device and this term by other portions, or a combination of both. So this is a general equation that lets us do some design calculations based on that without going to the brute force of CFD. Okay, so there's a couple of slides on how we define the aspect ratio. I've taken those from the paper, so you can have a look at those just for different arbitrary shapes. And then you'll see all this in the paper that I've uploaded onto Sula's, that there's a bit of discussion then on the differences and, you know, essentially demonstrating how useful this model is for different shaped stuff. And you see that if you look at the RMS, it's pretty good. Some shapes are not the best, but, you know, if you look at the max min, it's gone from, you know, minus 35% to 10%, so that's a bit of a stretch. But, you know, in other places, it's pretty good, you know. So generally in engineering, we're happy with plus or minus 10%, you know, for these kind of design calculations. Really happy with that. Okay, so it's quite a powerful approach. Just here you can see in the plots, you know, it looks really, really good. These are log plots, and So they're justified in using log plots here because you've quite a large range of numbers that they're using. They're going from 10 to 10 to the minus 3, for example. And they're going from 1,000 down to 10, 20. Okay, so they're justified in using a log scale in this. When you use log scales, things look an awful lot better than they actually are because the data is compressed. So it's kind of a classic trick that you'll see in final year project students, that they'll take data over like, quite a small range, maybe 10 to 20 or so, and they'll use a log plot to compress it because it looks better. You're only justified in using log plots when you have orders of magnitudes of change, so 1,000, 100, 10, etc. We're at 20 here, for example. We're up at 100 there. We're at 800 up there, so it's well justified in terms of using a log plot. But be aware that it's deceptive and that it makes the data in a graph look an awful lot better. So if you go back and check the hard numbers, there's an RMS. I like to look at the min max. So it's it's good engineering that all the data is available. And they've compared this to the literature, the Shah in London from 1978, which, funny enough, it's a paper that's cited an awful lot, and I've never been able to get my hands on it. I have to request it from the British Library, so it's one you'd think that would be out there, but I found it very, very hard to find that particular reference. But it is one that is cited an awful lot in the fluid mechanics textbooks. Right, so that's our general expression, and one of the things we can do is we can arrive at an expression for the entrance length. So how long should the entrance length be? And this is the result that we get. Okay, so it looks, again, a little bit hairy, but if I go back to the equation, again, I just need to write in that bracket. So what we're saying is, how do we arrive at this? If you set this term here equal to this term there. Okay, so what you're saying is that the two terms are equal. Okay, and if I go to a slide, I'll go back to a blank slide. Hear that. So what I have, I'll draw an axis again. So I'll do pressure drop off of P. Sure. Anyway, that's delta P. And we'll have L here. Okay, so I'll draw, let's go to draw a straight line down. Okay, so in fully developed flow, you get a constant decay. All right, so we'll call this the entrance region, LE. And what you would have is you'd have an additional pressure drop in that region due to the entrance effects. Okay, so if it was a straight pipe, fully developed flow, this is what you'd get. But because of the inertia and the different force bands, what you get is actually that. At this point here, the two are equal. So here you're using, I can't remember, it's C1 over L plus. We call it C1, and here we have C2. Okay, so FR root A. Here C2 is F root A. Okay, so you're using this calculation to calculate, and you get the pressure drop. At these 2 points here, it's the same. Okay, so you're setting the two terms to be equal. And if you do that, I'll just swap back to my slides, just make sure I get the right. Setting these two terms to be equal at that location. And if you solve then for L plus, but now L plus has a subscript H because it's the hydrodynamic entrance length. I use LE in the previous one there, so it's H is what's used in my notes and in the paper. Okay, so we're getting L plus is equal to that, okay, which is a constant times mass flow rate over viscosity. Okay, so again, if you have a higher mass flow rate, you have a higher entrance length. If you've a more viscous solution, it's a shorter one. If you have a less viscous solution or working fluid, the entrance length is longer. Okay, so that is how that expression is derived. And we can calculate for a given channel what the entrance region would be. Okay, we can calculate the L plus H and then convert that into an LH using the definition of L plus. So I actually don't think I covered what L plus was, so I'll just go back to that. Yeah, I skipped this at the start. So what is L plus? I mentioned before that it's a very useful expression. So that's what it looks like, but it turns out into this mu L over m dot. Okay, so again, viscosity of the fluid, you look that up. Length of the channel, that's the dimension that you should know. And m dot is the mass flow rate going through it. So it's a very readily measured and defined parameter in terms of the length of the channel, the mass flow rate, and a property of the fluid that is readily available. So this is an easy parameter to measure, so it's very, very useful. So L plus is quite straightforward. So if we have a value for L plus, which we're getting from that equation that we had, we can convert it into L by multiplying by the mass flow rate and dividing by the viscosity. So that's what we were doing up here. Okay, so we have LH is that value, okay, multiplied by the mass flow rate divided by the viscosity. All right, so that allows us to calculate what the entrance length would be in our channel. So if we're not sure how long it should be. Another final aspect which we'll cover for this lecture is the extent of duct length which is required for making a valid assumption of fully developed flow. Okay, so obviously it's a hell of a lot easier to do the calculation if we can drop this. Just forget about that term here and just use this bit, because we're just using the friction factor times Reynolds number. So our Poiseuille number is a constant, and we just use that for our calculation. Okay, so that's an awful lot easier. And that is a valid assumption with about a 5% error, which is fine for engineering purposes if we satisfy this condition. That the fully developed version of it is 10 times the L plus H. Okay, so if the L plus based on the length of the channel is 10 times the entrance region value. Okay, now I've covered quite a lot of stuff on this, so this is probably a lecture you'd want to go over a couple of times. I suppose the key learning points we want to get out are understanding the basis for this derivation, okay? That this term here is linked to the entrance region, to the developing aspect of the flow, and that this term here, and again, note the correction there on the bracket, corresponds to the fully developed region, okay? And that we're using the square root of the cross-sectional area as the appropriate length scale for this. And this is for any arbitrary shaped cross-section. So this is just a feature, although it looks hairy, it's got the hyperbolic tan in there. It just has aspect ratio inside there, it's got geometry. And this is tied to the Reynolds number. Okay, so it has, or sorry, not the Reynolds number, the mass flow rate. So L plus is mu L over m dot, so that gives us an idea of the extent of the entrance region, and this is the fully developed region. Based on this, we can calculate by setting both these terms equal. We can calculate a general expression for the entrance region. And we have a criteria that if, excuse me, I've gone too far ahead now. If this term is small relative to this, then we just focus on this term and we use that for our calculations. Okay, so one of the things you would expect to be able to do as an engineer, i.e. in your exam, one of the things I will assess is your ability to use this equation. Noting that this, again, every time I delete it, it's gone. It's 1 plus epsilon in brackets here. So being able to use this equation to calculate entrance lengths, to look at the relative magnitudes of the developing term versus the fully developed term. And the other thing you should be able to do is, and this is expected of you, is that once you've calculated this value here using this equation, to convert this into a pressure drop. Okay, so you should be able to, and this is coming from fluids 1, is to convert that friction factor into a pressure drop. Okay, so that's one of the things that you were expected to be able to do. And translate that as I will be asking you to do that in an exam to demonstrate that capability to me. Okay, so my job is to give you this equation and how to use it. On the basis of using this equation, you should be able to use a friction factor to calculate a pressure drop. Okay, so that concludes this lecture. I know it's just about half an hour long or whatever, but I have covered quite a lot. Don't be intimidated by the equations. They look a lot hairier than they actually are. They're much more straightforward to use. Please have a look at the original paper by Muzychka and Yovanovich that is uploaded onto Solus. You can have a read of that. What I have here is a summary. And if you have any questions, just come back to me on an email if there's something that I haven't clarified sufficiently. I can go through that with you, or send out an email or do another video just to elaborate more on a particular point. Okay, thanks for listening, and I hope you found that useful, and we'll talk to you again. Bye-bye.